Hey, welcome back to calculus. This is a big section, section 5.3. We're going to talk about something called the fundamental theorem of calculus. And it will turn out to be an extremely practical tool in calculating these definite integrals, which if you have done the homework and activities from section 5.2, then you know it's actually kind of a lot of work computing a definite integral by taking limits of Riemann sums. And even when we did it, we only did it for polynomials up to degree 3. And many of our functions, trig functions, exponential log functions, those kind of techniques of finding exact formulas for those sums so we can take limits of them are just going to be out of reach. So this fundamental theorem of calculus is an alternative for that. Okay, so let's get going. It's important stuff, like the name suggests. I'm going to tell you about the fundamental theorem of calculus. It actually kind of has two parts, and we'll look at one part at a time. And then I want to show you how we're going to use it to evaluate definite integrals. So hopefully just do lots of examples and try to illustrate applications of them as we go. But for the most part, we're going to just concentrate on kind of understanding how this theorem works and how the mechanics of it work. We'll soak in some examples of it in the next section, 5.4. Okay. So to introduce the first part of the fundamental theorem of calculus, we're going to talk about something called the area function. So what is the area function? So you're given, let me tell you what you just kind of start with. You're given this function f of t over here, okay? So it's kind of a thing, and it's the usual graph. Here's the graph of it. It's kind of increasing and then decreasing and increasing again. The axis is labeled t, right? So it's a function of t. Looks like it's non-negative. And we're going to define a new function. Its input variable is going to be called x. The domain of this new function is the interval from a to b. Okay, so for every x between a and b, I can write that over here. That's the domain of this new function. And what its output value is it's the area that's under the graph of f in the sense of the previous section, but only from a to x, as shaded in this picture. So g of x is the area of that blue shaded region. And you can kind of imagine that area changes as x changes. That's why it's a function of x. Okay, we can write that function down. We know integrals compute areas. F is greater than or equal to 0 on that interval. So if we integrate that function f with respect to t, the integrals in the variable, the input for f, but we're going to integrate from a to x. The upper limit of integration is a variable. All right, so I'm writing g of x, and it's very important that you understand this. Stop the video and think about it for a second. The input for g of x is that number right there. It's the upper limit of integration. So it's called an integral function, or we're just going to call it an area function in this context. Let me test you out on it a little bit. I've got a couple of quiz questions here. They're not really questions, but can we evaluate g at a? Do we know anything about it? What property of integrals? If we put in a right there, what's the integral from a to a of any function? You've already said it before me. So I click back for my pen. Yeah, it's 0. G of a is 0 because it's the integral, remember, from a to a. And we have an integral property that says that such a thing is always equal to 0. G of b is not really a question. It just says that it's the integral from a to b. It's the area under the curve. It's the thing we were talking about since we got into chapter 5. Okay, so that's what this area function is. As x changes, the area changes. The question that I want to ask about it is whether it's differentiable. You know, can we take the derivative of g with respect to x, and if so, what is that derivative? So I'm going to switch over to Mathematica here with you guys. Switching over. We're looking at a Mathematica screen here, and I know those labels are kind of hard to see. I didn't really get this squared away perfectly before I started making this, but on the left is your y equals f of t. If you want to write it down, that's your function f of t. It's graphed between 0 and, I don't know, 6, a little more than 6. And over here on the right is our area function, g of x. All right, so the axes over here are x and g of x. And what I can do as I move this slider, or I'm just going to kind of start this little movie, and I'll stop it for a second. But what you're going to see is the shaded area is going to grow under the graph of f. And as it does, there's the graph of g growing on the other side. So let me stop it for a second. Ignore that vertical line. That's just kind of because I have a slow computer drawing this picture. But when I stop it, this is accurate. So let's talk about what this picture means. This is our graph f of t over here on the left. I don't know if you can see the cursor, but the graph f of t is on the left. and you're looking at a shaded area under that graph. It looks like it's x is about equal to 1. Looks like it's the area from 0 to 1. So over here, the y coordinate on the area function is it's at x equals 1. And it looks like it's about, I don't know, 0.8. That's not the point, but the y coordinate on the graph on the right is the area of this corresponding region in the graph on the left. And does it make sense why that area was getting bigger? As x increased, the area was getting bigger because look, we're getting more and more area under the curve. Okay, let's keep watching. Okay, we're watching. We just crossed over, and let's stop and talk about it for a second. So did you notice something about when we passed x equal this intercept? When our function y equals f of t went from being positive to being negative? What happened over here in the area function? It maxed out. It had a local maximum. The area function stopped increasing and started decreasing precisely at the same x value where this shaded area switched from being above the axis to the negative below the axis, because below the axis is negative area, right? You got negative area down there. So it started decreasing the total. G of x is the total. That's interesting. So the moment that this function stopped increasing and started decreasing, that is, it had a local maximum at the place where f of t changed from being positive to negative. It's interesting. Okay, let's keep watching. Still accumulating area. The area function is dropping because we're picking up negative area. The area function just went negative. Why did the area function just go negative? Well, the total amount below the x-axis has now exceeded the amount above the x-axis. Okay, so we're in the red, quote unquote. Okay, keep going here. Accumulating, area is accumulating. And now what? Let's stop it one more time. When we started picking up positive area again, that is, as x passed that intercept on f of t, our area function stopped decreasing and started increasing. Right where f changed from negative to positive, the area function turned around. Yeah. So the area function has local extrema, exactly where this function f is equal to 0. And it's behaving kind of like, well, the derivative. It's behaving like the derivative. Right? The derivative of the area function would do precisely that kind of thing. Wouldn't it change from being positive to negative where the area function stopped increasing and started decreasing? Yeah, good. So it seems like the rate of change of this area function, g of x, does exist, and it's f. It's f. F at x is the rate of change. Okay, I'm just going to finish this by dragging the slider all the way over to the end. And ask one more question. Where the area function is now equal to 0. So what does that mean about the picture on the left? Well, it means that the total area of the regions that are above and below the axes they must be equal because they've canceled, giving a total of 0. Okay, cool. So that's as close as I'm going to get of giving what would be a proof of our fundamental theorem of calculus, at least the first part of it. So let me switch back to the whiteboard. I'm almost there. Switching back. And let's take a look at the statement of it. The fundamental theorem of calculus says that the derivative of that area function, if the integral from a to x of f of t dt, is just f of x. The rate of change, the rate of change of the accumulation of that area, net area, is just the height of the function at any given x. Cool. All right, so that's kind of an interesting fact. It's an interesting fact in and of itself, but what's really important to me about that is not just that fact, but it tells me that that area function is an antiderivative of f. Yeah. Remember when an antiderivative just has the property that its derivative is f. Well, the box formula says up there that the derivative of that function g is exactly f. So g is an antiderivative of f by definition. So that is certainly good news, because We're going to exploit that to our benefit shortly. Let's do a couple of real quick examples that kind of illustrate this formula. I could let you keep seeing it while we do some of them, but to calculate derivatives of these area functions, this first one, the f of t is this logarithm function. Well, the fundamental theorem of calculus says that that derivative is just that function, but evaluated at x. So it would be the log of 1 plus x squared. In number 2 here, watch out. The variable of integration is on the bottom, but we have a property of integrals that says if you put it on the top, that would just negate things. So that would just be negative x cubed times the sine of x, yeah? Why the minus sign? Because I had to switch the limits of integration. I didn't write the step, but mentally I had to swap those, and swapping those makes you pay with a minus sign. Cool. What about something like this? Look at this one. The upper limit of integration is a function of x. Yeah, so we have to use the chain rule. The outside function is our area function, right? This is just g, if you like. This is g evaluated at x to the fourth. X to the fourth is the inside function. So the chain rule, well, you take the derivative of the outside, but you evaluate it at the inside. So it would be the square root of x to the fourth plus 5. And then you have to multiply that by the derivative, oops, of x to the fourth. There you go. Yeah, chain rule. Cool. Okay. Now's the part I was excited about. Suppose you have some other antiderivative of this function little f. All right. Well, any two antiderivatives differ by a constant, right? So our antiderivative, any other one, it has to be our g of x plus some constant. And how could we find that constant? You usually need to know some value, but we know a value. Remember, we said that f of a was 0. F of a, the integral from a to a, is 0. So if f of not f, sorry, pardon me. G of a is 0. This integral, when you integrate from a to a, you get 0. Pardon me. So I must have the equation that f of a is 0 plus c. And that's just another way of saying that f of a is actually equal to c. So we know the value of the constant. So this other antiderivative has to be our integral plus that specific constant, capital F of a, whatever the antiderivative of f is. All right, so if we plugged b in for x, this equation would say that the integral from a to b plus capital F of a is capital F of b. And if I solved that equation for the integral, right, this is a number that we worked really hard to compute, taking limits of Riemann sums only for cubic polynomials, this integral of a function. You see what I'm doing? I'm just solving for it in this equation. To solve for it, I don't have to do very much. I just have to subtract f of a from both sides. So it's f of b minus f of a. And the miracle about this is, what was f? F is any antiderivative. Any antiderivative of the function little f. So it gives us a new way of calculating those integrals. And I promise I won't make you see it in my messy handwriting. Here it is stated nicely from your book. It's called the Fundamental Theorem of Calculus Part 2. And it says that if you want to evaluate a definite integral from a to b of some function, here the input variable is being called x, it's okay, then you just take any antiderivative for it and evaluate that antiderivative at those endpoints. And for abbreviation in our notation below, we'll write that as this sometimes. I'll write f of x with a vertical bar and then an a and a b. And by definition, I mean evaluate f at those two numbers and subtract in that order. All right, so sometimes I call this thing an evaluation bar. Okay, it's just kind of a shorthand for some arithmetic that we're going to do. I'll show you what I mean. So we can calculate integrals without limits. That's the good news. So let's do some. These are, you can interpret this first one as an area problem. I don't have a fancy computer sketch of this thing, but you guys know what a parabola y equals x squared looks like, and we're just computing the area between 0 and 1. I'll just leave it kind of a scribble like that. So we could do this by definition, Riemann sums. You've probably already done it. But if you want to do it with this fundamental theorem, you have to think like, well, what's an antiderivative for x squared? Well, we studied antiderivatives a little bit, and we have this rule that says that 1/3 x cubed is an antiderivative for x squared. And I don't have to add an arbitrary constant. I can just use this specific antiderivative, and then I'm going to put my evaluation bar and put the limits of integration. And then that reminds me that I need to take 1/3 of plugging in 1 cubed and subtract 1/3 of plugging in 0 cubed. All right, so I end up getting a third. So that integral, no Riemann sum, its value is a third. Fundamental theorem of calculus. Let's check out another one. This function on that interval, it's 1 over the x to the 2/3. It would look something like this, up to a scale. That region, it's not worth getting out Desmos. You can get out Desmos and graph it, but it's going to look something like that, and we're computing that area because it's non-negative. Oops, and I forgot my dx, pardon me. So again, fundamental theorem of calculus, need an antiderivative. Got to add 1 to negative 2/3, and then divide by that new exponent, right? So divide by a third is like multiplying by 3, and then evaluate. The evaluation bar is handy. You put 3, and that 3, since you're going to multiply it, you can factor it out. I personally like to factor it out. So instead of writing 3 times, I can just go, well, it's, plug in 8, plug in 1, and subtract. You can distribute that 3 back through there if you want to, or you can put it in both terms, but I like to factor it out. So it's 3 times the cube root of 8 is 2, cube root of 1 is 1, so it's 3. So that exact area is equal to 3. This is kind of a cool one. You guys have a little rough sketch in your mind of what the sine curve looks like. Yeah, there it is from 0 to 2 pi. So from 0 to pi, we're just talking about that area, right? Couldn't do that with Riemann sums. That we'd never find the formula for the sum of what to take the limit of, I mean. Sorry about that. But we have an antiderivative for sine. What function's derivative is sine? Careful, it's the opposite of cosine. The opposite of cosine has the derivative sine, right? Because the derivative of cosine is the opposite of sine. So 2 opposites make a positive, and then I need to evaluate that from 0 to pi. And I'm going to leave my -1 out there and say that's the cosine of pi minus the cosine of 0. So that is the opposite of -1 minus 1, and all those minuses, that ends up giving you 2. So that's kind of interesting. The exact area under one sort of half period, I don't know, one bump informally of the sine curve is this whole number. It's interesting. I've always found that interesting. Okay. Cruising along here, I'm just trying to show you the power of this. All of these things by Riemann sums would be tedious to impossible. Here you know what the exponential graph looks like. Oh, sorry about that. My pen thought I wanted a straight line. So from 0 to 1, we'd again be looking at some shape like that. Geometry can't do it because of the curved side. But with the calculus, the antiderivative of e to the x is itself, just as with derivatives. So evaluate, plug in the upper limit, plug in the lower limit, always get the subtraction in the right order. It's important. So e minus 1. Interestingly enough, you can get decimals for that. I'll just leave it like e minus 1. And then finally, we'll stop. We'll talk about some applications of these things in the subsequent section. This is just to get you going on computing integrals with the fundamental theorem. But let's do one where we kind of think about it as an area, and I don't hand it to you directly. So it's a region bounded by these 3 curves. So when I do something like this, I like to start by drawing the picture of the 3 curves. That doesn't have to be a super fancy picture. I'm just going to do kind of a hand sketch here. So give myself some axes, and then just kind of think about them one at a time. Y equals 0, that's just the x-axis, right? I just drew that. X equals 0 is just the y-axis. So I've actually already drawn, I'm writing, those are the equations of them, right? X equals 0 is the equation of the x-axis. Y equals 0 is the equation of x-axis, pardon me, I misspoke. X equals 0 is the equation of the y-axis. So we just have to graph the parabola 36 minus x squared. Well, that would be some opening down parabola with a vertex on the y-axis. It'd be shifted 36 units up, in fact. And so if we're bounded by those three regions, can you kind of see it? You have to be bounded by y equals 0 and x equals 0 and this parabola. So the region that we're talking about in this case turns out to be this thing over here, the right-hand side. It's not a very bright color. The right-hand side of the that sort of parabolic region bounded by the x-axis. Okay, so what do we need to know to compute an integral for that? Well, I mean, the integrand, the function that we're going to integrate, of course, is this parabola. So we know that we're going to be doing something like this. But what about the limits of integration? The lower limit of integration is clearly x equals 0. But what about the upper limit of integration? We need to know, well, what is the x value right there? So to find that out, we would have to set y equal to 0. And I think it's pretty clear that x is plus or minus 6 is the solutions of that. So that's our limit. And then we just have to compute the integral. So we take an antiderivative, one term at a time. Power rule. This is why the evaluation bar notation is handy, because your brain has to process this. What's an antiderivative for this function? Doing it one term at a time. So it's like a stopover point. Okay, got the antiderivative, remember to evaluate them, and then you got to just kind of, I don't know, get it down in your brain somehow. You put in the top number, then the bottom number. You subtract in that order. So in this case, I would have to take 36 times 6, which I believe is 216, and subtract 6 cubed over 3, which is 216 over 3. So that's plugging in my 6. And I'm being careful with parentheses, but in this case, plugging in x equals 0 in both cases gives 0. Right? So this thing ends up giving, well, 2/3 of 216, which I'll let you break down if you want to, but this video, I wanted to keep it kind of short. Okay, so in the next section, we're going to keep evaluating these integrals, but I want to do it in hopefully lots of interesting context for you as science and math students.